Hello, this is Mr. Jones, and we today are going to work on probably what I think is the hardest thing to do on an AP Chem exam, which is to explain why the periodic trends are the way they are. So this is usually what we call an essay question. Now in AP Chemistry, an essay question is not a long written response. Usually it can be answered in 3 or 4 sentences. But I do think it's one of the trickiest things to do. So that's what we're going to work on today. This video is going to assume you already know what all of these periodic trends are. So if I said to you, which has a higher ionization energy, chlorine or bromine, you know what ionization energy is, and you could predict which one has higher ionization energy is. And same goes with atomic radius. If I said I have cesium and strontium, which one of these two has a larger atomic radius, that you know what that is. You know that atomic radii are often measured in angstroms, that sort of thing. So it's assuming that you already know what each one of these is. So if you aren't aware of these, go back to the Review Center and look for those resources, or spend some time in your textbook looking up each one and making sure that you feel comfortable with them. Okay, so we're going to start with this question in green. It's a good example of a periodic trends question that AP may ask you. So the first ionization energy of bromine is 1140 kilojoules per mole, while the first ionization energy of chlorine is 1251. Explain this observation using your understanding of atomic theory. Now, what they mean by this is they mean dig into how many electrons, protons, energy levels it has. We are definitely going to have to boil down to those ideas. And there really are 2 approaches that you can take. You can either go down an effective nuclear charge shielding kind of approach, or you can use Coulomb's law. Now, when you go to look up videos that have answers on them later, you're probably going to find that I'm going to spend more of the time with this approach. And the reason in those early videos I went that way is because Coulomb's law is something that's kind of new to AP, but it's a really strong approach as well. So we're going to do, for this problem, we're going to do both of those approaches. Now, whenever I'm answering a periodic trends question, the first thing I do is I look at sort of the statistics of each element. In other words, how many protons does each one have? How many energy levels does it have? You could go into number of valence electrons. Sometimes that's important, so you might want to add that to it. But the first thing I'm going to do is they gave us data on the first ionization energy of each one of these. And the thing that I'm going to make a note of is that bromine had a lower first ionization energy. So bromine had a lower first ionization energy. Chlorine's was higher. Okay, just to make myself clear on that. And if I'm going to answer the question, I need to know exactly how many particles we have. One of the biggest mistakes students make is they don't say how many protons or energy levels these things have. You need to be specific. So chlorine, if you look up on the periodic table, has 17 protons in its nucleus. Bromine has 35 protons in its nucleus. As far as energy levels go, chlorine's valence shell is looks like it's in the 3rd period, so it is N equals 3. And for bromine, its valence electrons are in the 4th period, so N equals 4. Now that we have those basic ideas down, we're going to make our argument based on these particles. So if I were to say, why does chlorine have a higher first ionization energy? Well, it's either going to come down to the difference in number of protons or the difference in number of energy levels, but usually not both. Usually it's one or the other, and I'm going to focus only on the one that makes a difference. Now, let's look at both possibilities here. Is it possible that the difference in number of protons can explain the difference in ionization energy? Well, if you imagine that these electrons are outside of chlorine's nucleus that has 17 protons versus an electron that's outside of bromine's nucleus that has 35 protons, well, 35 protons, that's a lot more positive charge. So the attraction of the electron to that nucleus would be stronger because of that higher effective nuclear charge. That's what we call effective nuclear charge. More protons will pull the electrons in more. So that difference would make us think that this electron would actually be bound stronger and we'd expect bromine to have higher ionization energy, not lower. So therefore, that does not explain what we're seeing here in the data. We don't ever want to argue with the data. The answer must have to do with energy levels. So if the shells are out, or if the nucleus is out, it must have to do with energy levels. That if this is the nucleus of chlorine, and you have an electron that's 1, 2, 3 rings or energy levels out, versus in bromine you have an electron that is 4 energy levels away from that nucleus, you can imagine that the greater distance to the positive charge in the nucleus will cause this electron to be bound weaker. It just won't be held as strongly. There'll be a weaker attraction than in chlorine. And that does explain what we were seeing. So we know it does come down to the number of energy levels. And at this point, it's just a matter of making it a statement in about 3 sentences, maybe 4, that will explain it. Okay, so here's my answer. Bromine has a lower first ionization energy than chlorine because its valence electrons are in the 4th energy level, whereas chlorine's are in the 3rd energy level. The greater distance to bromine's valence electrons will result in a weaker attraction to the nucleus. Boom, and we're done. So when I look at my response, there are some things that are quite strong here that AP is going to require us to do, and these are the things that quite often people ignore, which is they want specific evidence. Which energy level? Now, we probably would not have had to repeat this here because you see we made this table up here. If you do this thinking on every single one of your examples, then you may not have to repeat it down here. So, but they do want specific evidence. The other thing is we use specific terms. We know that one of the most common ways that students lose credit for these examples is by not being specific. Let me give you an example. You can see how I said bromine has a lower first ionization energy than chlorine because its valence electrons are in the 4th energy level. It's a pretty common student response for people to say bromine is in the 4th energy level. Now, of course, bromine isn't in the 4th energy level. Its valence electrons are in the 4th energy level. So being specific about terms is the best way to make sure that you get credit. So this was one way for us to explain it. And you'll notice it always is talking about particles. Now this table, which sadly I think I'm going to have to reproduce on the next page, it's useful even if you do the Coulomb's law approach. Let's look at the Coulomb's law approach. So Coulomb's law, you may remember from first semester, is saying that the force of attraction between two things, like say for instance if you have a positive and a negative, the force of attraction can be calculated by using Coulomb's law. The force of repulsion if they have the same charge, like say for instance if you have 2 electrons, right, both of them are negative, it'd be the force of repulsion. So it can be used for all sorts of things. Q are the charges of 2 things, like maybe this is the charge of the nucleus and this is the charge of the valence electron. That's what those 2 charges would be. And R is the radius or the distance between those charged particles. So you can imagine if this was the nucleus and that was the valence electron, if it's further out, it'll be a weaker attraction. So same thing goes is I would make that list. You know that we said in the ionization energy, we said that bromine had a lower first ionization energy and chlorine had a higher first ionization energy. In this case, since we already know that the number of protons is not the determiner in this, we just skip that. And we were looking at the valence shell number. Well, for chlorine, we said that that was 3, and for bromine, we said that it was 4. And since we decided that this was the reason for the answer we were seeing on the first ionization energy, let's see how Coulomb's law could explain it. Well, because bromine has a lower first ionization energy, that means that its electrons are held weaker. The force of attraction between bromine's nucleus and its electrons is weaker. Well, why is it less? Well, we can ignore K, that's not super important. But if this is the nuclear charge and that's the valence electron, Well, the distance in bromine between its nucleus and its valence shell is much greater. If R is greater, and it's squared by the way, then the force of attraction between bromine and its electron will be weaker. And that's why the ionization energy for bromine is lower. So it's a very mathematical answer. And you notice we don't need to know K, we don't really need to think about charges. We just say the greater distance results in a weaker force of attraction. Now, don't leave it just as this. Of course, you would want to write a short paragraph explaining this, but this is a wonderful technique to use with Coulomb's law. Now, here are some keys to success. And this is the part that the reason we emphasize this so much is because if you essentially know what you're doing, there are a few things you can do to make sure that you receive credit. One is obviously cite specific numbers of electrons or protons or energy levels, number of valence electrons if you feel like that's the important thing. Don't be generic. Don't give that vague sort of this has more protons than that. They want detail. Actually answer the question. Very often you should either start your paragraph or end your paragraph with a restating of the prompt. It's a great way to avoid not answering the question. And this one sounds so insulting, but I will tell you from being at the AP reading that every year, I would say close to half the students don't answer the essay question. They give a lot of great evidence, they analyze it, but they don't actually answer the question. Make sure your argument is in agreement with the data. We saw that on the previous example that if you went down an effective nuclear charge route, talking about the nucleus, you'd be arguing against the data. Do not mention the octet rule. If we're saying, why does magnesium like to lose 2 electrons? The answer is not because it wants to be isoelectronic with neon. It's not because it would have 8 electrons. It's not any of those things. You're going to see an example coming up. Don't mention the octet rule. This is very frustrating to people because in first year chemistry we emphasize the octet rule a lot, but magnesium prefers to lose 2 electrons and it has nothing to do with wanting to be like neon. Don't use periodic table geography. If I said to you, which has higher ionization energy, fluorine or chlorine, and you say fluorine because it's more up or it's more to the right, that's periodic table geography. That's not an explanation. It's an observation, but it's not an explanation. The answer always comes down to the number of electrons and protons or energy levels. Don't talk about it being more up and to the right or down and to the left. So let's try it out on this one. The first ionization energy of arsenic is 947. I'm assuming this is kilojoules per mole. The first ionization energy of germanium is 762 kilojoules per mole. All right, let's do the first step, which is let's write down the stats for these 2 atoms. Okay, so I've summarized the data. It looks to me like arsenic has a higher first ionization energy than germanium. What that means to me right now is that germanium's electrons are easier to remove. Just making a statement to myself so that I don't get turned around and make an argument against the data. The electrons are easier to remove on germanium. Okay, now let's see if it has to do with the number of protons in the nucleus or the number of energy levels. Well, arsenic has, let's see, 33 protons according to that periodic table. And it has, let's see, 1, 2, 3, 4. It's in the 4th energy level, so N equals 4. For germanium, there are 32 protons, and it also has valence electrons in the 4th shell. So it could come down to the energy levels, but it's not looking like it. It's looking to me an awful lot like it has more to do with the difference in number of protons. So let's see, how could we make this argument? Well, if they have the same number of rings, that means that a 33 proton nucleus in arsenic would have a stronger attraction than the 32 proton nucleus in germanium. This electron will be much stronger attracted because there's more effective nuclear charge in arsenic. Now let's write out our paragraph. So I like my start here. The first ionization energy of arsenic is higher because its valence electrons are more attracted to its nucleus than those in germanium. Now, that has told the reader that I know what first ionization energy is, that it's the energy to remove the first electron that you're removing. But I haven't provided any evidence. And you might think, well, did my drawing here or did my writing here give me evidence? Well, maybe. That's the reason I want you to put this table in here, is because if you do that, the author can see, even if you forget to do it in your paragraph, they can see your logic up here. So always, always, always make this table. But yes, I would finish it off, and I would say, give the evidence that says why. And there we go. Arsenic has more effective nuclear charge than germanium because it has 33 protons in its nucleus, whereas germanium only has 32. I might say, if you're thinking, well, can I abbreviate effective nuclear charge? Yes, I think that and ionization energy the authors would accept, but you don't even need this term. It might even be better to say the valence electrons in arsenic have a stronger attraction to its nucleus because it has 33 protons, whereas germanium only has 32. That stronger attraction, always, always, always talking about attractions. I actually think that would be a better approach than what I went with here. Let's look at this one. The first ionization energy of nitrogen atom is significantly higher than the first ionization energy of a nitrogen -3 ion. Explain this observation using your understanding of atomic theory. So I want you to pause the video here, and I want you to list the sort of attributes of each one of these things, and then make your argument. So pause the video here, and then come back and check and see if you agree with me. So here are the things that I've written down. Based on this, that nitrogen atom has a significantly higher first ionization energy, to me that means that because it has higher first ionization energy, it is harder to remove electrons from nitrogen than it is from N-3. It's easier to remove those. And I'm just keeping that straight in my head to make sure I don't get turned around later. It clearly doesn't have to do with the number of protons because they're both nitrogens. They both have 7 protons. And it clearly doesn't have to do with energy levels because we know neutral nitrogen has 1, 2, 3, 4, 5 valence electrons in the second shell. And nitrogen -3 has added 3 electrons, so it's isoelectronic with neon, and therefore it has 8 electrons in that second shell, but they're still in the second shell. So since these didn't have any difference, I might actually go to the number of valence electrons. Clearly that has something to do with it. This is an unusual problem. So the neutral one we said has 5 valence electrons, and this one has 8 valence electrons, all in the second energy level. So it must have to come down with to these two. So why do we think that that might happen? Well, if you have more valence electrons in the second shell, remember electrons repel each other. There's a lot more repulsion between those electrons. So that's what I'm going to base my argument on. So there is more electron repulsion between valence electrons and N-3 because it has 8 valence electrons. There we go, citing our specific evidence. Like I said, if you do a great job making your table up here, you probably don't have to repeat it down here. If you don't make this table, you definitely need that evidence. So the repulsions will result in less attraction to the nucleus for electrons in N-3 and therefore a lower ionization energy. So in this one, the number of protons didn't make a huge difference. The number of energy levels didn't make a huge difference, and we had to go to valence electrons. But most of the time, it'll either be the number of protons or the number of energy levels that will explain the atomic radius or the periodic trend. Speaking of atomic radius, let's do this one. So I'll let you read it. I want you to pause the video and see if you can make a list of what makes these atoms similar and different, and then come up with an argument. All right, so I have boron, and I think the most common ion of boron is boron 3+, where it has lost 3 electrons. According to their data, boron has a larger atomic radius than boron 3+ does, and I find they both have 5 protons because they're both boron. But the energy levels are interesting. Boron, of course, its valence shell has 3 valence electrons in it, 1, 2, 3, and they are in the second energy level. But boron 3+ has lost 3 electrons, so it's gone from 5 to 4 to 3 to 2 it's isoelectronic with helium. That's why it lost those. Now, a lot of times people are tempted here to say something has to do with it wants to be like helium. Remember, octet rule stuff, we don't even want to go down that path. It doesn't want to be like anything. It's simply a matter of you can see it. It has to do with the energy levels. The valence shell of boron 3 plus is n equals 1. That means that its electrons are much closer to the nucleus, and that's why you're seeing this significantly smaller radius. And we're going to make our argument only based on this. We're not going to say it's like helium. It's not like helium. Forget about that isoelectronic stuff. It's useful for an understanding, but it's not an explanation. So this is what I've come up with for an explanation. The atomic radius of boron 3 plus is smaller because having lost 3 electrons, its valence shell is n equals 1, whereas the valence shell of boron is n equals 2. Therefore, the electrons in boron 3 plus will be closer to the nucleus. So that was one long sentence. It doesn't have to be, 3 or 4 sentences, but always, always, always write down the evidence that you have, because that way, if you accidentally forget to cite something down here, you won't lose credit for it. They really care about you knowing those differences. Each time I've been skipping the Coulomb's law argument, and I don't want to leave you with the impression that Coulomb's law isn't as effective. It certainly is. In the Coulomb's law argument, after you did all this, you would say, well, the electrons in n equals 1 are closer to the nucleus. Since they're closer to the nucleus, the radius is smaller. And you could say the force of attraction is higher, and therefore the electrons are sucked in closer. You certainly could do something like that if you wanted to as well. So Coulomb's law is perfectly fine, but I've been forgetting to give you an example of that.